All right. So what do I want us to look at today? So we already did the bingo. That was good. We now need to do something talk about a little about identity. And then we're going to talk about the system QB with identity plus Barkan. And we're going to then talk about Sheaves. And then this we're going to separate it in two. We're going to first talk about Kripke frames with equality, and then we're going to talk about Kripke sheaves. Now, sheaves are a very important word and term and notion in mathematics, in topology, in category theory, and everything. You don't need a background in any of those to understand what we're going to do today. If you know what they are, well, it's useful to see where this is coming from. But don't worry about not knowing what a sheaf is in topology or in category theory. I mean, Jan already knows what a sheaf is, so that's great. But other than that, let's not worry. So let's talk about the second thing we're going to talk about, which is identity. So what do we know that happens when we have, sorry, no, this is, what is this a recipe for? So I use the identity symbol. If you have first order logic and you add identity, what happens normally? It's a limited thing. You can stop being, and it becomes it's undecidable. So normally when we're working with first order logic and the identity symbol, there are various ways in which we can treat to recover part of this decidability and stuff. Now, curiously enough, in the realm of quantified modal logic, adding identity is going to solve some of our problems instead of giving us more problems that we have. So this is going to remain undecidable, and in fact, undecidability is a huge problem in quantified modal logic. But what I want you to tell you with this is that don't look at as identity as an enemy or something that's going to complicate things, but let's welcome it. And the way we're going to do this is first I'm going to present the system of first order modal logic with identity plus the Barkan formula, which is an important system. It's an important first. This is a language. Sorry. So this language is going to be the one with which we build the systems which are sound and complete with respect to a very simple axiomatic system and the semantics that we already had. Do you remember which were the systems of quantified modal logic that we saw last week that you could not show sound as that you cannot show completeness for? I'm gonna give you a clue, but it had to do with this fact that if you can look to them, they can look back. So how is this axiom named called? Yeah, symmetry. Yeah. You have to do how do you do transitivity? So this is symmetry, and this we normally characterize as axiom B. And we said that anything that contains axiom B being Q, KB, being QS5 is going to be incomplete. And that's, remember that it has to do with how we build the canonical model. Remember that the problem was that when we construct the L places, which was our notion of maximally consistent subsets, but in quantified modal logic, the problem was that when you define them, you need witnesses. And if you go to other worlds, which it's supposedly accessible to, in those worlds, there are going to be witnesses. They are supposed to satisfy the same formula, but you cannot make it as the witnesses coincide. So that calls for a notion of identity that we can ingrain into the axiomatic system. And if we put the Barkan formula to it, then we have it basically for free. So what I want us to see today is first the system QK with identity plus the Barkan formula. So this system, we're going to build it very fast. So if you want me to stop, please say so. But we're going to have our atoms. We're going to have a notion of identity between variables. Then we're going to have our conditional, necessary statements, and quantified statements. The axioms are going to be all the instances of axioms in K, in the modal logic K. We're going to have universal instantiation, which we don't modify it. Universal instantiation says that going to have backwards quantification. Provided X does not occur freely phi. And now here comes our axioms for identity. So the first thing we're going to add is, of course, reflexivity. And what is this? It simply means X is equals to X. We're going to have a version of Leibniz law, which, again, here we cannot define identity. We're going to give the axiom, so we cannot do this trick of saying two things are the same if they share the same predicates. But rather we said that if X is equals to Y, then you can replace every instance of X for Y in a formula that contains it. Our first notion of modal identity is going to give us but the rule of necessity of identity, which basically says that if X and Y are the same, then they are so necessary. And we at last have a notion of transword identity, so we can start crossing stuff in the bingo about this. We're going to have our Barkan. And we have the same rules that we had for first order modal logic. So rules same. Okay. All right, questions about this? I'm going to give, right, no questions. So what changes a little bit from our version that, sorry, the system that we had? In the first system, we had constants, and here we don't have constants right now. We're going to do all this with variables and the idea of free and bound variables. again, I assume that you know about this. I hope that you know it, but basically a bound variable is one that is tied to a quantifier appearing before the first appearance of the variable, and a free one is one that it has no quantifiers behind it. Then we're going to add constants, but we're only going to do that. We're going to do that at the model level, and when we're trying to prove the completeness. All right, so the first thing that we can do with this system is show the following. So I'm going to omit the subscript here. I hope this is clear. What is this? Does it look familiar? It should look familiar.
Just the Congress.
It's the Congress work of Modal. But what is interesting now is that we can derive it. So we can start from universal instantiation. Then we necessitate this thing. We distribute the box. Since we have this guy here, this guy here, we can basically do and then so I'm going to go step by step with this. So the first thing we did was to use instantiation, which remember that it's the good one or the not evil one from free logic. This one we have universally all the instances of it. Then what we have is the possibility of necessitating this via the rule for necessitation for normal logic. Then we distribute the box. Then we can use the universal instance of this, say because this is free here, and then we say we distribute this over here. Okay. I think there is a mistake in how I told you the rules. Oh no. All right, so the upshot of this is that.
Can I ask a question?
Yeah, sure. Sorry, I didn't see the hand. Sorry, just interrupt me.
That's fine. Okay. So we go from 4 to 5. We distribute the quantifier over the implication.
Yes.
But then we have basically we have for all x box for all x 5. Why can we remove the for all x in the start? Because aren't we supposing that if we add for all, does this not need to be a different, or no, it doesn't? Why can we remove it?
So this has to do with I think I didn't write this rule correctly. This one here, because I think what I wanted to write is this, if I'm not mistaken. I'm going to have to get back to you on that one. Thank you for pushing on it, but I think I miswrote it. But yeah, you're absolutely right. There's something fishy here. Yeah. Let me get back to you on that one. Is that okay?
Yeah.
All right. So everything that we built from QK plus Barker formula, one is going to have a notion of identity, and it's going to give us this necessity of identity, and at the same time, it's always going to satisfy Barker formula. So, and if we have these two, then we can have the convex Barker. All right. So now let's do semantics for this. And semantics for this is going to look very similar to what we had. And then first, we're going to have a frame, which is going to be a tuple. Let me write this as fancy F. We're going to have a world, some relation, and some domain. Then at this point, the world is going to be the same thing. The set of worlds is going to be the same. The relation is going to be the same. And for the domain, we need to say explicitly that it is non-empty and it is invariant. Across worlds. This is just another way of saying that we have constant domains. Now, Barkan is only going to tell us that we should have shrinking domains. But if we have converse and Barkan and converse Barkan, this collapses into having constant domains. So it's very important that we use this from the beginning, because otherwise our results are not going to hold. And for the idea of a model, we simply have our frames, and we have I, which is going to be our interpretation function that such that so I is going to be interpretation function such that I is going to assign for every predicate in each world a subset of the power set of the domain. So again, the extension of the predicates can vary across worlds, but we're going to have the same set of objects in each domain. So you can arrange them differently, but you always need the same. So now we're going to talk about variable assignment and satisfaction. So we're going to let G be a function for variables to objects in the domain. And since we don't have constants in the language, this is going to restrict it to variables. So we're going to use variables for this, which was different from the other system that we saw. And then with this, we can define truth. And truth is more or less what we already talked about. So in a model, in a world, we're going to say that relative to this assignment px of xn, so this is true if and only if the assignments belong to the interpretation of the predicate in W. All right. All right. important stuff to keep in mind is that now we have this, and this is true if and only if the assignment of x is the same as the assignment of g. I'm going to skip the other clauses, but they are just as you expect. So negation if the atomic one is not true. The conditional if either the first one's false or the consequent, the consequent is true. So if for the conditional, it's going to work that or and the universal and box operator is going to be exactly as you expect it to be. All right. So when we go to completeness, we're going to do a couple of nice things, but remember that we need to distinguish between the language, the base language that we start off, and then the language in which we do the completeness. Do you remember this step more or less? That you have to add the constants, the extra constants. So I'm going to give you a refresher just in case. Oh. Good. So first we start with our original language, L, and then we extend this L to a language L plus by adding countably infinite set of new variables. So this is going to be this bar, which contains an uncountably infinite set of new variables. And we say that sentences in a set of sentences of L plus is saturated or hence incomplete if it is maximally consistent and possesses the witness property. And remember what the witness property is. So the witness property says that if you have an existential claim belonging to the set, then you need to have a new one such that it is in the maximally consistent set. So the idea here, don't be tricked. So here the point is that y is going to be in our set of fresh constants. Well, x is on the original one. And yeah, everything can be made into a maximally consistent set and Henkin completes. Sorry. Yeah, Henkin complete, I can put it, or saturated. Don't worry about this. There's a way to do this via the enumeration trick that we saw with first order logic. Remember the enumeration trick? Can I see some knots here? Or either vertical or horizontal knots? It's okay. You remember what we did? Yes, yes, all right, good. But then we're going to do a crucial thing, which is going to be to and it is the fact that we're going to change our notion of domains, and we're going to give a notion of a quotient domain. So a major deficiency in the naive approach is that we were treating syntactic terms, variables are our constants, directly as objects. So if we contain an identity statement, the model must identify the objects X and Y. But we don't have a way of doing that in the domain right now because we just added a bunch of constants. So how do we reflect the two things are the same in the domain? And we're going to do it with the following idea, which is using equivalence classes. So the idea of this is that we're going to have we define the relation. How do you call this symbol in English?
Tilde.
Tilde, thank you. The tilde relation on the variables of L plus, like this. So you say that this, so X tilde Y, if and only if this formula appears in the saturated sets. So now this is going to give us the resources to talk not about objects, but of equivalence classes. That is, we take all the set of everything that is identical to a variable, and we can treat it as one single object. So for that, so the equivalence class of X, we're going to denote with X between these two bars, two single bars. So now with these tools, what we're going to do is have a new sense of a canonical model in which we're going to have the usual suspects. So we're going to have this canonical, and then we're going to have a canonical W, canonical R, canonical D, and canonical I. So changes. W is going to stay more or less the same. So now we have the notion of saturated maximally consistent sets in the new language. So remember that for this we need the new language. R is the same that we had before. So gamma R delta if and only if all the box formulas of gamma are in delta. And now we're going to make two changes, two very important changes to the domain and to the interpretation function. So the domain is going to be the set of equivalence classes such that X is in the new sets. So what are we doing with this? Again, we're just talking about the objects that are identical between themselves. And then the domain in the canonical model is going to be that. Compare this to what we did in the naive setting. In the naive setting, we could not do that, first of all, because we didn't have identity. But even if we had it, we didn't have an option of creating this equivalence class. Now that we can have it, now we're going to talk only about those objects. And then this basically means the interpretation is going to change a little bit. So for any world gamma, what we're going to say is that, so for atomics, we're going to say that it works like this. Right? And then identity has a similar clause in which we say that two objects are the interconnect interpretation identical for set gamma if and only if they are identical. There's a formula stating their identity in gamma. All right. So crucially, of course, again, this domain is fixed. So that means that everything that you're going to find in the world is going to be stated not only with the same individuals, but with the same identities holding between all individuals. This allows us to go over the problem that we had in the last week. And in the last week, we saw that this broke first in the existence lemma, and then in the truth lemma, we had problems. In the truth lemma specifically, so in QB, for instance, what we had is that we could have a necessarily existential predicate, so formula, for which we couldn't make it coincide the constants for which this was true. Now, since we have variables and the equivalence classes between them, we are able to go back and forth between the worlds without having to worry about which ones are there and which ones are in the other. Because not only now we have fixed domains or constant domains, we also have necessity of identity. So if you say that there are two equivalents, that there is two objects that belong to the same equivalence class, then necessarily, so in every possible world accessible from that, it is true that they belong to the same equivalence class. Questions so far? If not, then I want to jump a little bit. And okay, no. So first, let me tell you, there's a proof of completeness in the notes, and then there's in the notes also a explanation of how to work in these models for quantified KB, and so QB and QS5. So they are there. They're very interesting. Please take a look if you want to know more details of the proof. But I'm not going to mention it right now because there's a lot to cover. So now we're going to do the following thing, and then we're going to jump to identity in the models. So far, what we did was to give identity, give a symbol for identity in the syntactic approach, and we define a notion of identity. We prove that we assume that the necessity identity in a possible world implies necessary identity, and then we prove completeness. Now we're going to see a version of this story which is a little bit more flexible, but we're only going to see it for constant domains because it's the most well understood version of this. So maybe there is down the line a way to use these tools to give more powerful results for completeness for variant domains, but basically what these are for is to reintroduce constants into the language and then give a notion of identity between constants that does not depend on the interpretation of rigid designators. So we're going to see that this almost looks as variant domain semantics, but in order to work, you still need to give this something like a fixed or a constant domain interpretation. So we're going to see like this middle ground that is added the identity to the models itself. So for the first approach that we're going to see to this, let's talk about Kripke frames with identity. So what did we have in so let's do modal logic, let's do quantified modal logic with the identity, and then let's talk about Kripke frames with the quality. Sorry, I said identity here, but what I meant is equality. So KFE. So in modal logic, how many things do you have in the frames in traditional modal logic? Your frame is based on a set of worlds and a relation between them. And what do you need to add later with the domain? with the model is the evaluation function, right? In quantified modal logic, what did we add? In quantified modal logic, we added to this, we added the domains. And in quantified modal logic with identity, we stayed on the same place. But now in Kripke frames with equality, as the name says, is going to have an extra element, namely this equality symbol, which is double tilde. I don't know how do you call that symbol? But let's call it equality. So for KFEs, the idea is that your world and the relation between them, worlds and the accessibility relation, is going to stay the same. And this is where one starts like having hope. Oh, this is for variant domains, because now for data domains, we're going to have a system of domains which are indexed by the world. So to each world, we're going to assign different domains, but we're going to do it with a caveat, and it is the fact such that if W can access V, then the domain of W is contained in the domain of V. This is the expanding domains or the increasing domains restriction, which coincides with the converse Markov formula. And then lastly, for our equivalence, we're going to do more or less the same. We're going to say that this denotes a family of binary relations, each indexed to a world, such that for each W, double tilde W is an equivalence on DW. So this looks very cool because now we can say, yeah, maybe two things are going to be identical in one world, but we don't want to say that they are identical across possible worlds. In fact, things can merge, things can stop existing, and so on. But since we have the domain construct as such, the problem is that this is going to highly limit our the way we do this. So we cannot go with and say and have models in which we have less stuff. We have to at least have the same amount of stuff as in the previous domain. So to make this very, very easy to work with, what we have is the notion of hereditary equality. And this basically says that for a Kripke frame with equality and a relation double tilde must satisfy the following condition. For any two worlds such that they belong to the set, and for any two objects that belong to the domain W, the fact that W can access V and that A is equal to B in W implies that they are equal. Let's put some brackets here, that they are equal in V. So this is the second way in which we can obtain the necessity of identity for quantified modal logic. Oh, low battery. Yeah, low power mode. Let's do it. Any questions so far?
All Would right. You maybe scroll up to the previous page just 2 seconds? Yeah, there. There. Yeah, just the definition of the family. Yeah, I was just making sure that if this was a restriction or a definition, do we say that V sees another world if its domain is contained in that world, or is it if it sees it, then
domain is contained? So that first you have accessibility.
Yeah.
And if you have the accessibility, you impose this domain restriction.
Okay, thanks.
Right. So let's stop for 10 minutes. So I'll see you at 21, more or less. Oh, good. So Mateo asked a question, basically. Okay. So we moved from identity to Kripke frames with equality, what do we win? And the idea we were saying is that, so when we have just a language of first order modal logic with identity, then the necessity of identity, is basically forced upon us. Oh, you're not seeing, what did you do? You were just silently waiting for me to notice.
If they can see me, you're in the
All right. So yeah, I already told you that, but what the hell is working just now? We are experiencing technical difficulties. Please stand by. All right. So with first order modal logic, with some sort of identity defined in the language itself and using only variables, everything works fine. But this forces upon us the idea of rigid designators. What do we do when we move up the stair to Kripke frames with equality? We ideally and initially could make the notion of two things being equal in one world, but this equality not holding in other worlds, or even so, holding not at all. So in this first one, we have an identity. We have, let's call it equality for clarity's sake, an equality between D and E, and then we have C here alone. Then we have another one in which we have this, and let's say this is, we have F here, and then we have G here. They only increase. So what have we done with this model? We are violating this heredity of equality over how did I call it here? Hereditary equality, yeah. And this hereditary equality is telling us that if two things are equal in one that is accessible, they remain one. Here we're violating this. But the idea is that this, at some point, is going to allow us to arrive at a notion of identity which doesn't hold between all the objects, like rigidly, and it's not hereditary, thus giving us a nice semantics for variant domains. This hasn't happened yet, but the idea is that at some point in time it happens. I mean, I don't know of examples. Maybe it is just there around the corner, or maybe it's in a footnote in a paper by a Soviet mathematician, but I don't know. One of the sad things about doing this from a philosophical eye is that mathematicians doing this are only focused on constant domains. These are the main focus, so they give very little attention to variant domains. So yeah, I personally very much like the variant domains, but well. Any questions about Kripke frames with equality?
One last question.
Please, all of the
identity
all you
predicate, like the one that we know that we have always known, still is part of the language, right?
So yes, if you want, no, if you don't, but yes, because you can make it so that both collapse, for instance, but you don't need it in the language, because basically you are defining equality. You are not giving any axioms for identity. Okay. I mean, you can give them, but if you give them, then you need to include it in the language. If you don't give them, you can still have equality or identity or whatever you want, but you add it at the frame level. All right. Thank you. That was a great question. And now let's go for, I think it's the most interesting part of the course itself, which is sheaves. As I told you, super important topic in mathematics as a whole. We're not going to delve into that. We're going to talk about the concept specifically of a Kripke sheaf. And Kripke sheaves are just a way of gluing elements in a domain across worlds in a consistent way. So we're going to, instead of mapping objects to other objects in the same world, we're going to map them or glue them together with objects in other worlds. So a Kripke sheaf is going to be a Kripke sheaf over a frame. So we first need a modal frame, and we're going to, over that, we're going to have the tuple phi, and it's going to have your worlds, relations, your domains, and this transition maps, which I'm going to denote with the Greek letter rho. Can you see that it's a rho and not a p? Difficult, but if you're wondering when I write something, if it's a rho or a p, please tell me. So W is what you expect. R, for clarity's sake, let's say that it is reflexive and transitive. And let's put just symmetric to spice up the stuff. And we're going to say that D is going to work just as in Kripke sheaves with equality. And now we're going to talk about this as, so if we have a DW, so a domain for a particular world, we're going to call this the fiber or stock in W. And then rho, rho is going to be a family of transition maps such as the following. So rho of WB is a map from the domain of W to the domain of B for all worlds for all worlds in the frame. So what is this telling us, and what is the intuition behind this? So you're going to have a function that is going to say that for every domain, for every item in the domain W, it's going to give you an inheritor of that item, sorry, that object in the next world. So the intuition of this is that if we have a domain W and a domain V, and this is W and this is V, then we have to, and then we have that A, B, C, D, D, E, F. Then the idea is that we can define the maps in some way. Now, if the map is total, it is injective, and it is surjective, basically you have constant domains. If you start switching between what is going to happen, then you have constant domains, you have increasing, you have shrinking, or you can have varying domains altogether. Again, for the sake of clarity and the presentation of this, we're just going to see cases in which this transition map is total. So for every object, it's always defined. It's going to be injective. So what injective functions mean and surjective. So injective for each one, you're going to have each one from the domain. Codomain, no, let's not talk about domain and codomain here because we have two domains already. So each one from the you can also say image and pre-image, right? Yeah, so for every item in the pre-image, there is one unique item in the image, and all you map them all to items in the image as well. Again, this sort of like hopes like, oh yeah, this is great. We can have variant domains. Yes, probably, but if you are very strict with how you do it, you end up with constant domains, which is what we're gonna do today. Basically, we're only gonna look at. But at restriction, we're going to add some restrictions to the transition map, and it is the fact that it respects identity and it respects composition. So this is where your categorical brains should start tingling. Because with this you can define a category. Yeah, this is a notion of morphism, which respects identity and composition. But we're not going to talk about this. But basically, identity means that for all worlds, this is the same is the identity function on dw, and composition means that if V is accessible from W and V accesses U, then guess what happens? The transition, always forget that I should write. If you compose the transition of W to V, you take it and you compose it with the transition from V to U, what do you get? The transition from W to U. In Christian terms, this means that if there is a world, there are three worlds, and in this world, you are able to map C to D, but it also happens to be the case that A is mapped to C. That means that we have W, we have V, and we have U. That means that the inheritor of C in D is the same as the inheritor of W in U. Sorry, of C in the inheritor of C in U is the same as the inheritor of A in U. We good? So now the problem is that we have to give an adequate notion of a semantics, right? And it's going to work as you expected, and then, but we are going to, we have a model, and the model is defined in terms of this new frame. I can't call it frame, but it's a Kripke shift, remember? And then you simply add the interpretation or the evaluation function, however you want to call it. And then what is going to be difficult is to define truth. Because now we have all this idea of like things going across worlds. So how are we going to define how things work with the box operator. And basically, what we're going to say, and what one needs to say, is that if box phi D is true, then for an object D in W, phi must be true of the inheritor of D in all accessible possible worlds. I'm going to write this more formally and then explain it again so that we can make it more clear. So for all V such that W are D, it must be the case that, and here is where the level S, so you're going to have the mapping, the transition mapping, composed with the variable with the assignment. And then I'm going to zoom out in a second. Give me a second. So what we need to say again is that if something is necessary with respect to one object, so that means that the inheritors of that object across all accessible possible worlds also satisfy the formula phi. If you see the notes, there's a problem with the notation there, but I'll fix it. All right. Is this cool or what? All right. Now, there are a bunch of very interesting results that I will not go over, but what I want to do now is to tell you a little bit about the relationship between them. You can see there's like some results I'm going to talk. Then I want to talk about a subclass of Kripke sheaves and then show you a very important result in the area. But again, I'm not going to have time to go over it, but it's in the notes. So we should basically be now asking ourselves, what is the relationship between Kripke frames with equality and Kripke sheaves? So KFEs versus Kripke sheaves. Well, in this very strict setting where we have, on the one hand, the hereditary condition for the Kripke frames with equality, and on the other one, we have total injective and surjective transition maps. Guess what? You can find for every Kripke frame with equality a sheaf, and for every sheaf, you can find a Kripke frame with equality. So you start, I'm going to tell you more or less, both sides how it works. Proofs, the notes, I'm going to sketch how this works. But the idea of this is, I hope that you now understand why I was so keen on saying, and we need to basically do this fixed domain stuff. Because at this level, they're going to work more or less the same so that we can then import a lot of very powerful results from Kripke frames to Kripke sheaves. And that is basically just a completeness result. So well, it turns out basically that these two ways of generalizing the semantics are very intimately related, and actually we have like this two representation theorems. So the first theorem is going to say that from a Kripke sheaf, we can Kripke frame with equality, we can go to a sheaf. And this basically what we're saying with this is that the following. So let F be a Kripke frame with equality, then there is a Kripke sheaf phi of F such that the logic that you can do here is the same as the one you can do here. All right, so the proof idea is the following. What do we have in sheaves that we don't have in Kripke frames with equality? Basically the transition map, right? Because we have this notion of local identity, and with the hereditary condition, we can expand that. So we're going to make use of both facts to make it. So the idea is that we construct the quotient of the domains in KFE, and then we define the fibers of the sheaf as quotient sets. That basically means that we're going to have a new fiber defined on the basis of the domain in the Kripke frame by using the equivalence that we had, and we're going to do the trick that we did with the identity of making everything into a equivalence class. So there we already have everything nicely packed. Now what we need is to say how this is going to work for the transition maps. And for the transition maps, we also need to define and we're going to simply say that rho WV is going to be a map from the new fiber W to a new fiber V, and so naturally, and then we define that for any class D in V such that belongs to the fiber, let rho WB of D relative W be the class relative to V. You've been for what second?
The main thing is, I feel like with KFEs, we still had the possibility of merging objects, right?
No. Yeah, it was. We had it until I told you hereditary condition.
Okay, so we can have more.
You can have more.
So the domain can increase. But I thought the only restrictions we had is that if they're related, then related stuff in like the first world must still be related in the second world,
Yes. So
right?
yes, but now that means that if you add more stuff, then you're going to define new equivalence classes with those, and then in the next one, you're going to respect that as well. But you have a restriction and restriction with this. That is the thing I told that I think I skipped over this a little bit, and is the fact that if you add axioms for identity and collapse them with the equivalence symbol that we have in KFEs. So if you add axioms for identity and the hereditary condition, then you satisfy Barkan and converse Barkan, and therefore you have constant rings.
Okay.
So the idea is that all of what we have talked about, it will be very nice if we had it for varying, increasing, or decreasing domains, but we're only focused on constant domains. So I can promise you this result for constant domains.
Okay.
So if you add more stuff and you start merging them, yeah, maybe the mapping has to be different, and you cannot be as easygoing. Oh yeah, you just map it to the next class. Okay. Great. This stop sharing. But is that clear? Sorry.
Yeah, I guess I just missed that we had that constraint of concept.
Yeah, that is so. The point of this lecture, which I hope it is more or less clear at this point, is that we're focusing on constant domains, not because they're very interesting per se, but because they allow us to recover all these nice results from which we can then start, okay, what if we tweak this, what if we tweak this? You're right? And yeah, so this is for Kripke sheaves, for Kripke frames with the quality to Kripke sheaves. And then more or less related to what we were talking. So remember that we have hereditary condition. What the hell is this? Screen broadcasting condition. It's not. You can see it. They cannot see it.
But I think it's not. Are we not recording? Or?
No, it is recording.
Okay.
It's logged out.
Recording in progress.
Right, we have the hereditary condition, and with the hereditary condition, we ensure that the map rho is going to be well defined. So if two objects are equivalent with respect to a world W, then they're going to map it to the same class in a world V, which is accessible. So this means that, so if A on W, this basically means that if we have this, then A, B, but with regards to B, are going to be mapped to the same class. So we still have the same amount of objects there. They're still there.
Yeah, no, I got that. It was more the injectivity that was confusing.
Okay. Do you want to?
Well, it's just like the way if we only have like this direction of the implication,
Yeah.
and it seems to me like you could have, like you wrote there, that like the number of stuff that is equal increases. Like
Yeah.
there is more stuff that is now a part of the same equivalence class, so you can have two distinct equivalence classes that get mapped to the same thing and then break into two.
Yeah. So with increasing domains, let's say yes, and you can have the same results, and hereditary only take you one away. But if we are interested, for instance, in soundness and completeness, then you're going to have to introduce identity at some point. And then you map it to the equivalence that you have in the frames. So, yeah, like I would love to go deeper into this, but the point is, if you want a system that behaves nicely and you can clap and say, yeah, we proved that it's sound and complete, you need all of these requirements that make everything constant, right? So if we remove the hereditary condition, that would be very cool. I mean, so with only the hereditary condition, we have what you just said. Without it, we have even more freedom to do this kind of stuff. But yeah, then it becomes very complicated to manage. Although very, very interesting, right? All right. So I told you that there is another the other way around. It is it's in the notes. I don't want to talk about this because I still need to cover flabby sheaves, and it is how we're going to basically recover completeness, and then basically remember what we did at the beginning of the lecture. We said if I give you Barkan in the syntax, if I give you Barkan, give you identity, then you're golden. And now the question is like, do we have the same thing that we have with the frames, but now with the sheaves? So I told you here's an axiom system. Oh, by the way, I didn't look up the thing that Magnus asked me. I'm sorry. I'm going. I'll drop you a line, guys, later about that. But the idea is to see if we have the same result with respect to sheaves as we had with respect to normal Kripke frames in the beginning, that we saw in the beginning. And the answer to this is yes, but only with a class of Kripke sheaves. So we're going to talk about, I hate the name of this, but it's called flabby and locally flabby sheaves. So we're going to try to translate the requirements of the Barkan and converse Barkan to the Kripke sheaves. So with the Kripke frames, with the quality, we did it with the hereditary condition, and this one we're going to basically make it not only the hereditary condition, but see how it works for the other way around. So sheaf is flabby, and it is locally so. If every transition map is surjective. And then it's just flabby. Maybe I should have explained this the other way around. Sorry. It's going to be flabby if it is rooted and every individual in any domain is an iterated inheritor of some individual from the root domain. So this should tell us a lot of how the identity across worlds is going to work like. So if something is flabby, then everything has an origin point. And if it is locally flabby, it means that all the transition maps are essentially surjective or onto. This means that you're always touching with the transition map all the objects in the new domain. And if you are touching all the objects in the new domain, and more of that, if you're touching all the objects in the new domain, basically you cannot add anything new, right? You can maybe take something from it, but you cannot add anything. And the idea of local flabbiness is that we have a rooted world. That means that there is a world for which modulo the accessibility relation everything is related to it. Sorry. Yeah. It means that there are not arrows pointing at it, but it has access to all of them via the transitivity and symmetry. Yes, transitivity and reflexive accessibility relation. So it looks more or less like this. Sorry, that came out a little wrong. I'm sort of confused at this point. But sorry, do you understand the local flabbiness intuitively? Sorry, about this being a root. Do you? Yeah. Sorry. Oh. Yeah, and then
Why is it called flabby?
I have no idea. It is the silliest name.
Right. Can we call it like tree-like or something else?
Yeah, I guess you can. I'm gonna ask someone that maybe knows the answer to this, but yeah, I agree. It's a horrible name. Yeah, tree-like sounds better, but maybe this. I mean, I don't know. Maybe you want to say more than tree-like because this is not only seeing the frames as a graph, but also the transition relation, and maybe flabbiness is something that is important in another area of mathematics, but I don't know. Well, right. So the idea is that yeah. So validating the Barkan formula, it is equivalent to being flabby. For rooted sheaves, it's going to be, if it is locally flabby, then it's going to be satisfied, validate the Barkan formula. I'm super tired. Let me just finish with this today. There is a complete proof for this in the notes, and this is called Suzuki's theorem. Suzuki's theorem basically is gonna go back to what so go full circle to what we have talked today, and it basically says the following thing. So if we let a logic be any quantified modal logic that has the Barkan formula, if L is complete with respect to Kripke sheaves, then it is complete with respect to Kripke frames. So the idea of this is that we understand what are the limitations of this theorem. Basically, we are assuming the Barton formula. And we are just saying that if you have the sheaf for that system, for that logic, and it is complete with respect to it, it is also going to be with the frame that you can build from the sheaf with the procedure that I told you about a little bit. So I'm feeling not so well right now, so I need to stop there. But let me just ask you if there are any questions that you have right now. Okay, then I'll leave it there. I'll stop the recording.